Alright. So, now next point. Okay, so this is our our version 0 op amp. Let us again assume that this is ground. We already know what to do when we have to operate this with a single supply. Now, the question is, what are the signs of the op amp? So, this we claim to be an op amp, correct. So, let us call this terminal A, let us call this terminal B, and let us call this terminal Y. So, is A the positive terminal of the op amp? Is it the non-inverting terminal or the inverting terminal? How will we figure out? Okay, you yank A up. If that node A goes up, what comment can you make about node X? Okay, some fellow says goes up, some fellow says goes down. So, if node A goes up, node X goes up. If node X goes up, what comment can you make about the drain of M5? Goes down. So, if node if the drain of M5 goes down, what comment can you make about Y? Decrease. Alright. So, is A the inverting terminal or the non-inverting terminal? Inverting. Alright. So, this is a this box, I mean assuming that VDD and ground are all okay, this is basically a claims to be an op amp. So, these two terminals come in and one terminal comes out, correct. Okay. Now, how do we know that this is actually a good op amp? How do we know that this is good enough? Alright man, you guys go and order an iPhone from Amazon, okay, you will get some packet, okay, you will open it, this seems something like a phone, how do you know that it is not, I do not know, I mean some Chinese imitation that the seller is trying to give off to you? How do you know it is not a within quotes toy iPhone which looks like an iPhone but is not a cell phone? It could be hammam soap with cell phone pasted on it. How will you know? What will you do? What will you do? You will turn, you will attempt to turn it on. If it turns on, that doesn't mean anything, right? It could just be some bunch of lights that they put inside. It could not necessarily a cell phone. What will you then do? You will try to make a phone call. You will try to download something. You will try to install app, right? If everything works, right? I mean, if this box does everything an iPhone can do, okay, even if it's hammam soap with picture of iPhone pasted on top of it, it is an iPhone, isn't it? There is no way of knowing. I mean, you are just taking it on faith, okay, all right, okay. Same thing here. This is I mean, you said I want an op amp. I have given you a triangle with two input terminals, one output terminal, right? How do you know it's an op amp? It seems like he says, well, input impedance is infinite, output impedance seems 0. Good, I mean, here is my 10,000 rupees, give me the op amp, right? What will you do? I know this guy is saying taste it. No, that's not. Not taste it. You must test it. Okay, all right. So what will you do? You put this op amp in all possible circuits that you can think of, and if it does everything that it's supposed to do, then it's very likely an op amp inside the box, right? The simplest circuit you can think of, as he points out, is voltage follower, because you don't do anything, right? You just have to connect the output Y to the inverting terminal like this, okay, and then what will you do? You apply Vi and then some voltage, okay, and what do you call? Remember our discussion. This Vi must now be, because it is our op amp is operating between VDD and ground. That Vi must be centered around VDD by 2. So basically, we add VDD by 2 plus some sine wave, right? Some, I am going to call this some A sine omega. correct? I mean, is this logical or no, right? This is what you will do, correct? All right. So, now what do we do? So, which is why we needed to figure out which was the inverting terminal and which was the non-inverting terminal. So, where will we put, where will we connect the output Y? This was A. So, we will go and connect Y to A, correct? All right. Then what will we connect at the gate of M2? VDD by 2 plus some A sin omega. All right. Okay. So, for argument's sake, let us assume that the overdrive of all transistors is the same, some delta V. The first thing to do is the operating point, right? I mean, if this is let us say A is 0, then what comment can you make about this guy? This becomes 0, all right. So, if assuming the op amp is working properly, right, what comment can you make about the potential of A? Let me mark all these voltages in some other color, blue. Okay. What is the potential quiescent operating point? What, assuming the op amp is working properly, if this is 0, what will be the volt potential at A? VDD by 2, very good. If this is VDD by 2 and all the transistors are operating in saturation, what comment can you make at about that potential? What is the current to the transistor? M5, guys. I2, we assume that all transistors have the same gate overdrive when operating in saturation, and if the op amp is working as intended, correct, what comment can you make about all the transistors? All the transistors must be working in saturation, right. So, what should be the so if all devices were in saturation, what comment can you make about the gate of M5? Have the same overdrive Vg of M5 must be at what potential? Vt plus delta V. All right. Okay. So, and what comment can you make about this character, that voltage? Why? Yeah. So, the output is VDD by 2. So, and that is a VCVS of gain 1. So, it means that the input must have been VDD by 2. All right. Okay. So, we found the potential of at all nodes. I mean, this node potential is nothing but VDD minus VTP minus delta V, or VDP plus delta V. Correct? All node potentials are no. Now, we have to verify and see if these potentials were all found predicated on the fact that all transistors are operating in the op amp is working well, which means that all transistors are working in saturation, right, and therefore the gain of the op amp is close to infinity. That is what that is the assumption behind which, using which we have found the potentials everywhere. Now, given that these are the potentials, we have to go and verify our assumptions, namely all the transistors are in saturation, correct. Okay. So, let us go device by device. M1, if it kind of helps you, maybe you can just take some numbers. So, say VDD is say 5 volts, Vt is say 1 volt and delta V is say 200 millivolts. Okay. Whether it's NMOS or PMOS, Vt is 1 volt, let us assume. Okay. Now M1, come on, quick. Gate is at 2.5, drain is at. So, are we good with M1? Is M1 in saturation? You two fellows in the back. Yes, okay. So, that is green. What about M3? Why? Gate and drain are connected to each other. Okay, all right. What is the what about say M4? What is the potential at the at its drain? Vt plus delta V 1.2. What about so is M4 in saturation or not? People. Kuldeep, sure. Okay, so M4 is good. What about M5? The gate voltage is at 1.2, the drain voltage is at 2.5, so that guy is a good, right. What about M2? The gate voltage is at 2.5, drain voltage is at 1.2, all right. So what comment can you make about M2? It is not in saturation. Okay. All right. So what is the conclusion of our story? Hey, I mean, is this going to work as an op amp or not? Because assuming it works as an op amp, we went and found all the node potentials everywhere, the quiescent voltages everywhere, and we find that already there is a device in trouble. It cannot be in saturation, which means that you cannot have a high gain, which basically means that therefore this is not an op amp. Okay, right? Just because the input impedance is infinite and output impedance is 0, and if all the devices operate in saturation, right, then this is an op amp, right? Just like how, okay, just because something looks like an iPhone, it's not an iPhone, isn't it? So clearly using an NMOS common source amplifier, hey, what can I say? It didn't work out. Okay, all right. And now hopefully we understand why. I mean, intuitively can we see why you are choosing? I mean, can somebody look at it and say, I mean, this was a stupid idea to begin with. I mean, why did we even bother? Okay, if you have a NMOS common source amplifier, what comment can you make about the quiescent voltage at the input? Will it be close to ground or will it be close to VDD? This NMOS transistor expects a quiescent voltage which is close to ground, right? So if you cascade the NMOS common source amplifier directly with the differential pair, then the differential pair's output voltage, quiescent output voltage is constrained, has to be close to ground in order to be able to make it, to be able to ensure that M5 is happy, correct? Okay. In other words, the output quiescent voltages of the first stage and second stage are simply not compatible, correct? Okay. So I mean, it does not mean that the second stage is bad or the first stage is bad, right? It is just that these two stages are simply not compatible, isn't it? Okay. So so if you want the two stages to be compatible, what do we want to ensure therefore? I have spelt out the root cause. What is the fix? Don't jump steps. The two stages are not compatible, correct? So, what is the fix? You have to make sure that the quiescent voltage that the second stage needs at its input is acceptable to the first stage's output, correct? Okay. So, what suggestion can you make? So, clearly the NMOS, what is the problem with the NMOS second stage? The input quiescent voltage that the NMOS stage needs is close to ground, but what we actually need is, a common source stage whose input quiescent voltage is close to VDD, right? Okay, so what comment can we make about the second stage? Therefore, what should we do? Yeah, I know, that's what I understand, but what suggestion do you have? You replace. I mean, see, the answer is a no-brainer, simply because remember that NMOS and PMOS transistors act in a complementary fashion. If a certain amplifier stage made with NMOS transistors, requires, say, a low input quiescent voltage, if you just convert the NMOS stage to a PMOS stage, the behavior will be complementary. So, it will need an input voltage which is high. So, what do we do now? Therefore, you remove the NMOS. Okay. Now, somebody help me fix this diagram. What should I do? We need a common source. So, active load will eventually be an NMOS transistor, but at this point we will just basically say I2. All right, and this goes here. Okay. Another alternative we could have tried was, if we insisted on using an NMOS common source stage in the second stage, what could we have done? Do you understand the question? Now we've gone and changed the second stage from an NMOS to a PMOS one. If we insisted on keeping the second stage as an NMOS common source amplifier, is there something we could have done to make the output levels of the first stage and the second stage compatible? So, basically we could have as well used a PMOS input differential pair with an NMOS active load and drive a NMOS common source second stage. Do you understand now, man? Right? Okay. So, now let us see if this works. So, if this is VDD by 2, all right, quickly let us go through all the quiescent voltages. What is this voltage going to be now? Quick. VDD minus VT plus delta V, all right, and all the other potentials remain the same. So, let us figure out quickly device by device if this is okay. So, M1, okay, not okay? Okay. M2, the drain potential is close to VDD. It's actually VDD minus, in our example, for instance, we are at like 3.8 volts, whereas the gate of M2 is 2.5 volts. So, the drain is much higher than the gate. So, the M2 is okay. What about M3? M3 drain and gate are shorted anyways, never a problem. M4, the gate potential and the drain potential are the same, so M4 is not a problem. What about M5? Sorry, this is now M5. What about M5? What is the drain potential? VDD by 2. Okay, so basically M5 is also. Is that clear? Okay. So, so basically, uh, this is a workable amplifier. Okay, and if so, this just make sure that the quiescent points are all seem to be okay. Then, when we add a sine wave at the input, I mean, there will obviously be a maximum amplitude before which some device or the other goes into the triode region. Okay. And what comment can you make about so now that we have fixed the second stage, what do we do about the third stage? A common drain, I mean, this you can use either NMOS or PMOS. So, let us say this is I3. All right. So, now what comment can you make about this potential? As still VDD by 2. What is this potential? This is VDD by 2 plus VT plus delta. Okay. Now, when we add and so this is basically so this is a workable CMOS op amp, okay, except that we have to worry about stability, which we will do later, but at this point from a incremental DC gain point of view, where the DC gain is large, this is the inverting terminal, this is the non-inverting terminal, and this is a two-stage operational amplifier with a gain of the order of GMRO whole square. All right. So, we will stop here, we will continue in the next class.